Today we are going to talk about one sample hypothesis testing. So what a hypothesis test does is it challenges a already accepted statistic. So a null hypothesis is a statistic that is widely accepted or is considered the status quo. So it is something that has already been established by some population. It is denoted using the symbol H sub O. Null means to start at the beginning. And so when we're doing a hypothesis test, we do need a place to start from. So what exactly am I challenging? And our null hypothesis will always have a proportion equal to something because that's already been established. So P is going to be equal to a given value. And our alternative hypothesis is going to challenge the null hypothesis. It's something that we see that could be different, and we're going to challenge that null hypothesis using what we call an alternative hypothesis. And since a alternative hypothesis challenges a null hypothesis, we're going to see if our p-value is greater than, less than, or it could just not be equal to what is currently accepted or what is currently our status quo. Now, when we run a hypothesis test, we are doing it for one reason and one reason alone, and that is to be able to reject our null hypothesis. So saying that our null hypothesis is wrong. So we're not proving that anything is right. In order to prove something to be absolutely correct takes a lot of work, a lot of time, and there's a lot of things that go into it. However, you can prove something to be not true. So you don't have to particularly have enough evidence to prove one thing to be correct. You just have to be able to supply enough information to show that it's no longer correct or accepted. So we can reject the hypothesis or the null hypothesis, or we are failing to reject the null hypothesis. So we're not saying, okay, what I'm doing is right and what you're doing is wrong. What we're just saying is, okay, what I thought is not wrong. So we're not proving right, we're just proving wrong. So I'm not wrong, you're wrong, or we're saying you're not wrong, I'm wrong, kind of deal. And in order to do that, you have to have two conditions, and these are just kind of rules of thumbs. It's very hard to prove something when you don't have enough data or enough evidence or enough statistical data to prove something in terms of your population. So what we want to do is make sure we have enough of a sample size that we're getting significant data. So not saying, oh, out of 10,000 people, there are just 2 people who believe this. That's not significant, okay? But if I had a population of 10,000 and I took a sample size of 1,000 or even 500, I would want at least 10 samples that prove or that are there for my proportion, population proportion, and the difference of it. So kind of like a yes and a no. So we run our conditions by saying the number in my sample times my population proportion should give me an expected outcome of at least more than 10. And vice versa, if I took my sample proportion, what is the expected outcome for people that don't fit into the population proportion? And I want those to be at least greater than 10. And that lets us know, okay, we can run a normal distribution here. I have enough data to run a normal distribution. So in order to do a hypothesis testing, you need 5 pieces of information. You need a population proportion, which is provided to you in your scenario. You also have to have a sample proportion, which is provided for you in your scenario. It's usually given to you as X amount out of X amount, so you have to turn it into a decimal. You also have to have your sample standard deviation, which you are going to calculate yourself. Using these three pieces of information, you can come up with a z-score, and we use z-scores in standard normal distribution where everything is standardized. So then we're going to use that z-score to get a p-value, or to actually run the hypothesis testing. And based off of that p-value, we want to compare it to something known as a level of significance. So it's sort of like our confidence intervals, but we want to see if our data lies outside of that significance. And so we want our p-value, or our proportion under the curve in our normal distribution, to be less than the significance value. If it's less than it, that means, well, this data is absolutely going to reject a hypothesis, a null hypothesis. If it's greater, then you're failing to reject it. So that level of significance is very, very important. So we have 5 pieces of information that we are going to be looking at and using to run a hypothesis test. So let's look at a first example. So a concern was raised in Australia that the percentage of deaths of Aboriginal prisoners was higher than the percentage of deaths of non-Aboriginal prisoners, which is 0.27%. A sample of 6 years of data was collected, and it was found that out of 14,495 Aboriginal prisoners, 51 died. Do the data provide enough evidence to show that the proportion of deaths of Aboriginal prisoners is more than 0.27? So the first thing that we are always going to take a look at is what is your parameter? What are the things that we're actually looking at? And in this case, we are going to be looking at the deaths of Aboriginal prisoners. So that is my parameter. That's the thing that I'm looking at. Now, I have to have a null hypothesis, and that is our current status quo, our currently accepted information. And in my scenario here, it's deaths of Aborigines or Aboriginal prisoners is currently at 0.27. So my hypothesis is equal, or states that my population proportion is going to be equal to 0.0027. So I'm just turning my percentage into a decimal. And my alternative hypothesis, the thing that I want to look at, is if the proportion of deaths of Aboriginal prisoners is more than that. And so as my alternative hypothesis, I would write, I want to check and see if P is going to be greater than 0.0027, because I want to know if the deaths of Aboriginal prisoners is more than 0.027%. So in order to run a hypothesis, I want to first check for my conditions and make sure I have enough sample size and sample data to accurately display a normal distribution. So I'm going to use N times P. N represents my number of trials, or my sample size. And so in this case, I had a sample size of 14,495 and a population proportion of 0.0027. And I want that to be greater than 10. And if I number crunch it, I do get a value quite more actually than 10. So that's one condition that checks out. But I also want to check and make sure I have enough sample for non-Aboriginal deaths as well, and I want that to be greater than 10. So 14,495 times 1 minus P, and that is significantly greater than 10 as well. So I do have enough sample data to run a normal distribution. And in order to run a normal distribution, I do need a z-score, so we are going to be calculating that. So I'm going to start with my 4 basic pieces of information. I'm going to look at my population parameter, which is given. I'm also going to look at my sample proportion and my sample standard deviation. So if I come back to my word problem, my sample proportion is going to involve the 51 out of 14,495. So 51 out of 14,495. And when I calculate that as a decimal, I'm looking at 0.0035, and I'm going to be rounding to the 4th decimal place today. The greater number of decimal places that you choose to round to will give you a more accurate analysis, but just as a rule of thumb, I'm just going to do up to 4 decimal places as a rounding. So I've got my p hat value, and now I need to calculate my standard deviation for my sample, so my sample standard deviation. And so we're going to use the formula p hat times 1 minus p hat all over my sample size, and I'm going to take the square root of that value. So the square root of my p hat, which is 0.0035, times 1 minus that, which is 0.0035. And I just leave it as that 1 minus that p hat because when I put it into the TI-84 calculator or a calculator app, it does allow me to build it in just like that. So that's how I'm going to use it. All divided by my sample size, which is 14,495. And that will give me a standard deviation of 0.0005. So now that I have p hat, and my standard deviation, I can calculate the z-score that I need in order to run a normal distribution. So my z-score says my sample population minus my or my sample proportion minus my population proportion, all divided by my sample standard deviation. So since I have those values already calculated out, I can set that up by saying 0.0035 minus 0.0027, all divided by my standard deviation for my sample, which is 0.0005. Lots of very little decimals here, but as long as you are filling in based off of your formula, you can use any sort of advanced calculator to calculate those out for you. So when I calculate that out, I do get a z-score of 1.6. So in this particular sample, the deaths of Aborigines prisoners is 1.6 standard deviations above the mean, but that doesn't necessarily mean it's out of the norm or it's enough to reject my null hypothesis. So I am going to run a normal distribution using Desmos, and in a normal distribution you have a mean value of 0 and a standard deviation of 1, and our z-score can be used to calculate the minimum or maximum probability or proportion of data. So since my alternative hypothesis was looking to see if there were more Aboriginal deaths in the prison, I am going to set my z-score of 1.6 as my minimum value, because I am going to see, or I want to see what's the proportion of it being greater than that. And I am going to use that data with Desmos, which is a online graphing tool. It's also got some really great features in here for normal distribution. So under the functions key, distribution, I'm going to go normal distribution with a mean of 0 and a standard deviation of 1. So standardized normal distribution. if I click the little magnifying glass, it's going to give me my normal distribution curve or my bell curve, where it says find cumulative probability. I'm going to check that, and I'm going to go ahead and put in a minimum value of 1.6. That minimum value is going to give you the proportion of shaded area under the curve, which is going to be significant in testing your against your level of significance. And so right now my sample data does fall at 0.0548, so I am going to round up. And so I write that as my p-value is going to be equal to 0.0548. Now at this particular point, we are going to compare it to that level of significance. Now the level of significance, if not stated, is generally 0.05. Again, it will be stated if it wants anything different than that, but usually if it falls within the outer edges, the outside 5% of your two tails of your bell curve, then that would be enough to reject a null hypothesis. So since my p-value is greater than my level of significance, again my p-value was 0.0548. Unfortunately, because that value is greater than the level of significance, it's not enough to reject the null hypothesis. So we say that we fail to reject our null hypothesis. So even though the Aboriginal deaths are higher, they don't fall outside of what is considered normal. They're a little higher, but there's not enough evidence to prove that there's only 0.27% of Aboriginal prisoners dying. But we're also not saying that that is exactly the truest value. We just don't have enough evidence to create a alternate kind of belief or idea. So we say that we failed to reject the hypotenuse or the null hypothesis. So let's take a look at another example. In 2001, the Gallup poll found that 81% of American adults believed that there was a conspiracy in the death of President Kennedy. 2013, the Gallup poll asked 1,039 American adults if they believed there was a conspiracy in the assassination, and found that 634 believed that there was a conspiracy. Do the data show that the proportion of Americans who believed in this conspiracy has decreased? Test at the 1% level. So in this particular scenario, we want to know if the conspiracy, the people who believe in the conspiracy has decreased. And again, here is that 1% level. So in the last example, they did not state a percentage level, but this one does. And so that's what we're going to test to. So the first thing I want to do is identify my parameter. What exactly am I looking at? And my parameter here are American adults who believe in the John F. Kennedy conspiracy. So my null hypothesis, or what is currently accepted, is that about 81% of Americans, adults, believe that the conspiracy, believes in a conspiracy for the death of President John F. Kennedy. And what we're trying to challenge is that that particular belief has decreased from 2001 to 2013. So in order to challenge this, we want to make sure we have significant data. So we're going to use n times p, and we want to make sure we have more than 10. But we also want to check for 1 minus p times n, make sure we have a value greater than 10. So my sample size here, we did check for 1,039 adults. I'm going to go ahead and underline 634 because I'm going to need that later. So I had 1,039 adults, and 81% of that is going to absolutely be more than 10. And 1,039 times 19 is absolutely going to be more than 10 as well. And I've number crunched them, so I just know that I have more than 10, which is good, which means that I can work a normal distribution. So now that I have my null hypothesis and my alternative hypothesis, I'm going to identify my p hat, and my s in order to run a z-score for my normal distribution. So my population proportion has been given to me is 81%. My p hat, or sample population, says that 634 out of 1,039 individuals believe that John F. Kennedy was indeed, the murder of John F. Kennedy was indeed, or the death of John F. Kennedy was indeed a conspiracy. So if I run those as a decimal, I'm looking at 0.6102, and my standard deviation is p hat times 1 minus p hat, all divided by my sample size. So I'm going to use those values, square roots of p hat, which is 0.6102, times 1 minus 0.6102, all divided by my sample size, which is 1,039 individuals. And I'm going to put that in the calculator as is. I'm not going to try to simplify anything. I'm just going to type it in as is. And I get a standard deviation of 0.0151. So now that I have p hat, and sample standard deviation, I have enough to calculate a z-score. So remember that the z-score is p hat minus p, all divided by s. So 0.6102 minus 0.81, all divided by my sample standard deviation, is going to give me a z-score of negative 13.23, which is a very large z-score, so I know that that is going to be very, very close to 0. So I am going to use normal distribution, the mean of 0 and a standard deviation of 1. And my z-score I'm going to use as either my maximum or my minimum. And I want to see if the population, or if, yes, the sample size proves that, like, less Americans think that the death of John F. Kennedy was a conspiracy. So if it was less than 81%, and so I'm going to use that as my maximum value because I want to know what's less than negative 13.23 z-score. So I'm going to use Desmos. So I'm going to go to functions, I'm going to go to distributions, normal distribution, and I have a mean of 0 and a standard deviation of 1. So here is my normal distribution curve, and I do want to use a maximum value of negative 13.23, so using my z-score. And I can see that my probability is 2.9 times 10 to the negative 40. So that what that's stating is that there are 39 zeros in front of that too, which means that this is significantly close to a proportion or probability of 0. And again, that proportion is called our p-value. So our p-value is equal to 0, and if you remember, we were doing a level of significance at 1%. So my p-value is 0, and 0 is absolutely less than 0.01, so turning that 1% into a decimal. And since my p-value is less than my level of significance, this is enough to absolutely reject the null hypothesis. So it's using all of the information that we have learned to develop this thing called a hypothesis test that either rejects a null hypothesis, rejecting what's currently accepted as being normal, or it's not enough information to reject what's currently being our status quo or what is currently accepted as normal. So we're either going to be able to reject a null hypothesis or fail to reject a null hypothesis.